So hello everybody and welcome. I'd like to introduce Dr. Gil Shomron. He received his BSc and PhD from the Faculty of Engineering and Electrical and Computer Engineering, the Technion, in 2014 and 2021 respectively. His thesis is about conventional computer architecture mechanism and new instances in the area of deep learning. His work was published in various conferences like Micro, NIPS, ECCB, and CAL, and also papers, journals. And Dr. Gil Shomron is currently a deep learning architect at NVIDIA. So Gil, welcome, and please go ahead.
Gil, we cannot hear you.
Yes, thanks. So, thanks, Freddie, for the introduction, and thanks for inviting me. My name is Gil Shomron. I will present today my work that I've done during my PhD with Professor Weiser at the Technion. So nowadays I work at NVIDIA as a deep learning architect at the end-to-end training team. And the title for today is Embracing the Resiliency of Deep Neural Networks, Rethinking All Mechanisms. Okay, so in our research, we were talking about the new environment of deep learning. Besides the impact these models have on the applications they are being used for, and besides the paradigm shift some may call software 2.0, in which the software behavior is data dependent, from a software perspective, it has some unique characteristics compared to conventional software. So in our research, we leverage those characteristics to achieve execution efficiency. Also, since our research group back then was historically working on general purpose processors, I was highly inspired by known concepts from CPUs, which we were trying to rethink and map to this new environment of deep learning. Also, while scrolling through YouTube one day, I saw a talk by Yale Pat, which is a well-known professor at Austin, and there he mentioned that phrase, old paradigms, new instances, which is a very similar way of thinking that we had during that research. And you can find it also on YouTube afterwards if you like. So the agenda for this talk, we will talk about SMT, and I will say a few words about value prediction, not the conventional general purpose ones, but okay. So let's start with SMT, simultaneous multithreading. So first of all, we're talking about matrix multiplication, which is at the heart of neural networks. It is known that there are many zero values during DNN computations. So in practice, it means that the execution hardware may be idle quite a lot, since a multiplication by zero is zero, and adding zero to something is that something. So sparsity in DNNs can be in activations and or weights. With activations, the sparsity is usually inherent in the model. It is dynamic and it is unstructured, which means it is harder to leverage compared with weight sparsity. Now, weight sparsity is usually a result of training with regularization or pruning process, which can be either structured or unstructured. The weights are static, so they are easier to leverage in hardware, all the more so if it is structured. At the diagram below, we demonstrate the percentage of zero-valued activations per layer in ResNet 18 with ImageNet. On average, there are 50 zero-valued activations during inference. So this is just to get a feeling of how many zeros are there. So we said matrix multiplication. Each element of the output matrix is the result of a dot product, which is a summation of multiplications of activation by weight. Now consider a single multiplier, which receives a pair of activation and weight and yields their multiplication result. Now, as I said in the previous slide, it is enough that one of the operands to be equal to 0 to make the multiplier idle. So to mitigate idleness, we share the multiplier. So two streams or two threads or just two pairs of activation and weight are the inputs to a single multiplier. We use 2 in this example, but conceptually it can be any number of threads. Now, if the first pair does not need the multiplier because one of the operands is equal to 0, the other pair can use the multiplier freely and vice versa. The main question is, what happens if the two pairs need the multiplier at the same time? Before we talk about the different solutions, a word about why we call it SMT. So we call it SMT since conceptually there are a couple of computational flows and shared resources. But the usage of SMT here is a bit different than what we know from general purpose. Here, SMT is data dependent or data controlled, as I wrote in the title. Whereas in the conventional SMT, the instructions are getting in the execution units as a function of the execution unit state, meaning if they are free or not. In addition, I will show later that we employ this SMT on structures that are not general purpose at all. Now, back to what happens on contention. So the first solution is blocking SMT, which is rather a conventional solution. So in this solution, if contention occurs, one pair is going to the execution unit while the other one waits. If there is no contention, the two pairs are getting in while only one uses the execution unit. The data that needs to wait is stored in buffers, and if they are full, we initiate back pressure, which means that signals are sent to upstream units to let them know not to pass data. We demonstrate this idea on top of a systolic array. So on the left, we illustrate the structure of a systolic array with two threads. The black arrows represent the two threads data, and the dashed arrows represent the backward signals for the back pressure. In addition, within each processing unit, there are the buffers I was talking about, an arbitration mechanism, and multiplexers. Now, on the right, we simulate the utilization and speed up of a systolic array as a function of the input sparsity for a number of thread volumes, as you can see in the different colors. Now, intuitively, we can see that when there are more zeros, the utilization decreases. And when we increase the number of threads, we decrease the probability that a processing unit will be idle. So therefore, the speed up increases.
Gil, you can use your pointer, if you want.
Right. I'll do it in the next slides, thanks. So we simulated this structure on some different neural networks and input matrices, but at this point, I'd like to jump right into the insights since we don't have a lot of time today. So what did we learn from this work? The blocking approach fits better for training since the relative overhead of the SMT logic over floating point-based units is smaller than the relative overhead over int-based units. So that's the first thing. And the second thing is that when it comes to integer-based execution units, there is not a lot of room to maneuver since the integer units are relatively small to begin with. But still, how can we proceed? How can we employ this SMT concept on top of integer-based units and get better performance or easier hardware implementation? So what we haven't done is specifically target neural networks. Notice that this work can be employed on any set of matrices. And if we are talking specifically about neural networks, we might take into consideration their unique characteristics, and one of them is resilience. So for example, it is common to quantize image classification CNNs from floating point to 8-bit integers without training and without accuracy degradation. In addition, the application itself may be tolerant. For example, in this example, let me the pointer. So in this example here, yeah. In this example here, is it important that the car will be classified in 86% and not 84%? Or is it important that the bounding boxes will be slightly shifted to the left or to the right? Well, this is obviously user dependent and application dependent. But the point is that there is some tolerance for data corruption in these networks. What may lead to what we know is the blue screen of death in general purpose and operating systems, for example. So in this work, we use something we call non-blocking SMT. In this idea, we leverage networks resiliency and we use on-the-fly quantization, as we'll see in a second. So how we leverage resiliency? In the previous example, when there was a thread collision, we let only one thread to access the shared resource and put the other one in a buffer. Here, we are not stopping anyone, but instead we squeeze the threads in. Because we don't stop anyone, we name it non-blocking SMT. So what does squeezing mean? So instead of stopping one of the threads, in this example, we let both threads go into the shared resource by momentarily and locally decreasing their precision. For example, if we talk about 8-bit integers, to squeeze both threads in, we decrease their precision from 8 bits to 4 bits. Notice it occurs dynamically only when contention occurs. I would also like to point out that this is an example of a non-blocking mechanism. There might be some other ideas in the future. With this mechanism, there is a speed up potential as the number of threads. So why that squeezing in is practical? So in general, a single 8-bit by 8-bit multiplication is equivalent to 2 4-bit by 8-bit multiplications. And also it's equivalent to 4 4-bit by 4-bit multiplications. So meaning that we can implement hardware that is capable of a single 8-bit by 8-bit or 2 4-bit by 8-bit or 4 4-bit by 4-bit with almost the same logic. Now, I would like to make a quick review about the conceptual differences between the conventional SMT and non-blocking SMT. So first of all, SMT performance benefits are not deterministic. Instructions are entering the execution units as a function of the microarchitecture state, which is highly application dependent. On the other hand, with non-blocking SMT, the speed up potential is deterministic. As for the second point, SMT is blocking versus non-blocking SMT, which is non-blocking, obviously. And the third point is that with SMT, the computations are precise. And with non-blocking SMT, we make some approximated computations. Bottom line, we trade the non-deterministic performance with some impact on model accuracy, as we will see in the next slide. We measured non-blocking SMT impact on a number of CNNs with ImageNet. In the table, we present the baseline accuracy in floating point 32, int8 quantization accuracy, and then the relative accuracy with 2 and 4 threads. In ResNet 18, for example, we see a degradation of 1.3%, and with ResNet 50, we see 0.4%. For 4 threads, there is obviously a more significant degradation in accuracy. Since our non-blocking SMT mechanism is backward compatible, we can set specific layers to run with different number of threads. So we show we can trade accuracy for speed up, as we can see in the graph here on the right. In that graph, we took ResNet 18 with 4 threads, and for each run, like for each dot, we set a different number of layers to run with 2 threads. Then we measured the accuracy and calculated the speed up. This is in the line which is green. The orange line presents the same measurements with ResNet 18 version with 14 unstructured weight pruning that we've done prior to that execution. Since 40% of the weights are now zeros, there is a smaller chance for collision, and therefore the model accuracy is better. So the orange line is below the green line. This is the y-axis is accuracy decrease. As for the implementation, we employed non-blocking SMT on top of a systolic array. On the right, you can see the before and after. To enable non-blocking SMT, we need a controller that checks whether there's a collision or not and set the appropriate control signals to the multiplexers and the quantization units. And obviously, we need the flexible multiplier that is capable of 1 8-bit by 8-bit or 2 4-bit by 8-bit multiplications. We implemented it to get energy and area estimations. The results are only for the core systolic array without any memory hierarchy. Now, the blue here is the baseline, which is a conventional systolic array. The green here is the non-blocking SMT with 2 threads, and the orange one is 4 threads. The performance, as I already mentioned, is deterministic. With 2 threads, there's a potential of 2x, and with 4 threads, a potential of 4x. As for energy, there's a decrease in energy because effectively during execution, non-blocking SMT does less computations, since when there's a collision, we do the computations in lower precision. And as for the area, it increases due to the additional logic of non-blocking SMT. What are our takeaways from this work? So first of all, when it comes to non-blocking SMT, we showed that we can leverage unstructured sparsity in rigid structures such as systolic arrays. Remember, in systolic arrays, there's almost no control. Everything is super deterministic. The data needs to flow and reach each processing engine in the exact time. So it is not that trivial to optimize these kind of structures. But still, what can we do next? So we can still reduce area overhead, and we can still reduce the impact of non-blocking SMT on the model accuracy. And that's what we did in our next work. We call this one SPARC, which is sparsity-aware quantization. In this work, we are looking on a similar yet different operating point. We examine only the activations. If someone wants to prune the weights, he or she should rather do it in a structured pruning algorithm so it can be leveraged in levels of the stack which are higher than the microarchitecture level. Once we are examining only the activations, we can offload a lot of logic outside the processing engines. In addition, we can do more complex dynamic quantization scheme. And in the next slide, I'll show you what we are doing. So as before, we look at pairs of activations. If the first pair does not need the multiplier, then the other can use it, and vice versa. If there's a collision, we choose 4 bits based on a sliding window. In the previous work, we chose either the 4 MSBs or the 4 LSBs, and as you can see in the picture here on the rightmost illustration. In this work, however, we enable more fine-grained bit selections. In picture B, we enable also the middle window from bit 2 to 5, meaning 3 options. And in illustration A here, we enable all window options, meaning 5 options. We can see in the example below, let's say we have that number here, 000111011. For the 2 options, the 3 MSBs are equals to 0. And yet we still pick the 4 MSBs here, even though there's a clear redundancy in that pick. As we have more windows, obviously we will be more tied to where the data really begins. But as always, more options means larger hardware eventually. This table summarizes the accuracy results of this work, the previous one, and post-training quantization methods. We compared our accuracy results to conventional post-training quantization methods. I think it is pretty clear that non-blocking SMT, in the table here is, we call it CSMT, and Spark, which is this work, has an advantage in terms of accuracy since it avoids quantization and as much as it can by leveraging sparsity. Spark, however, also has a downside, which I'll mention later. But anyhow, we can see that Spark and non-blocking SMT achieve better results compared with post-training quantization methods. And we can see that Spark achieves much better result than our previous work. By the way, we also conducted experiments on 3 bits and 2 bits, and results are rather good. Again, thanks to the dynamic quantization. As for hardware implementation, I'll say a couple of words. We implemented the processing engines of a systolic array and a dot product unit inspired by NVIDIA Tensor cores. It seems that the sweet spot is 3 options, like 3 windows, since the accuracy in that operating point is rather small in most cases, and the area overhead is 20 or 30%. If we compare the 5 options to our previous work, CSMT or non-blocking SMT, then the area overheads are pretty much the same, but Spark's accuracy is far better. Our work on Spark showed that in retrospect, choosing either the 4 MSBs or 4 LSBs was not the best choice. But anyhow, implementing Spark on our first non-blocking work would have increased area overheads even further. I said Spark has a downside. The disadvantage is that as opposed to quantization methods, Spark does not save in memory footprint, since for each 4 bits, additional control bits are required. For example, given the 5 option configuration, it will cost additional 3 bits. We can maybe work around that thing as well, though. We do have an idea that can be further researched. We're done with SMT, which was a large portion of our work. I do want to say a couple of words about value prediction before I wrap things up. So about value prediction. So in CPUs, value prediction is a way to predict the outcome of the load instructions. Once you predict the value, you can avoid pipeline stalls due to memory accesses. Freddie here and Avi knows a lot about that. We argue that DNNs, though, may be better fit for value predictions. First, quantized networks have a specific set of values that each activation or wait can receive. And second, when we have ReLUs, we know that negative values will turn to 0. So a 0 value prediction can actually predict negative values in general. Another difference with CPUs is, again, resiliency. You can't have a misprediction in CPUs. After you speculate something during execution in CPUs, you check afterwards that you were correct. And if not, you go back and do things again. Now in DNNs, since there are so many computations with parallelism, it might not be feasible to check for correctness. Also, it might not be that important. Obviously, it depends on the application and the user. But as we saw with SMT, mispredictions will affect the model accuracy and not the execution performance. So it's about that trade-off. So what we've done with value prediction is output 0 value prediction in convolution layers while leveraging spatial correlation. So spatial correlation or spatial locality in our domain. In vision problems where inputs are usually real images, surfaces are usually continuous until you reach an edge. We want to leverage this feature to try and predict regions in the output feature maps that are equal to 0. We assume that if there's a group of zeros in the output, there are probably more zeros around that area. as you can see here in the pictures, which are brought from real feature maps. In general, like conceptually, we propose a three-stage mechanism. First, here, we compute only part of the output feature map. Second, given the partially computed feature map, we try to predict which of the remaining output activations will be smaller or equal to 0. And finally, we compute the activations that are predicted as non-zero and skip those that are predicted as 0. By doing so, we can potentially skip entire convolution operations. During our research, we proposed two implementations. On the right, we compute the output feature map in a diagonal pattern, and then for each window in the output, we examine its diagonal. If the diagonal values are equal to 0 after review, we predict the entire window to be 0 valued. Otherwise, we compute the activations in that window. The implementation on the left here is conceptually similar, but instead of a static diagonal classifier, we propose a lightweight CNN that does that. We present here the results of our two methods and the results of other related work that we compared to. I would like to point out that our CNN-based solution proposes many operating points with accuracy speedup trade-offs. We chose here those that match the related work, so we have a common ground for comparison. In general, we can see that our solution achieves better performance than previous works, although there is still place for improvement in future work in that area. So to conclude, the two concepts here, we were working on, SMT and volume predictions, they lead to that approximate computing fits like a glove to deep learning. We can achieve a lot of performance by cutting corners from time to time during execution. Second, in general, our work and many others show how much closer the algorithm and application are to hardware, and I can see that even more nowadays in my work at NVIDIA. And third, the feeling I got during my work is that this entire field, either from the algorithm side or the hardware side, is really in its beginning. So there are many, many interesting things to do. And yeah, thanks. Not sure if there's time for questions. Freddie will tell. And I'm doing publication as an NVIDIA employee. We have GTC today, so you're welcome.
Thank you very much, Gil. It was very, very interesting. Thank you very much. And folks, if you have any questions, feel free. Just send them at the Q&A tab, please.
And as we wrote in the Q&A, we will release the videos and the PowerPoints as the speakers allow us on the webpage that we'll send you soon. So thank you meanwhile, and Chaim, do you like to share your
yes
slides?
Yes, of course. 1 minute.
So meanwhile, while Chaim is sharing his slides, so a few words of introduction to Chaim works. So Chaim was mine and Alex Bronstein, PhD student, and he graduated about almost a year ago. Now he is working in our lab as a senior researcher and do a lot of works on many interesting fields. Recently started working mainly on graph neural networks. So this talk will be about graph neural networks. Thank you, Chaim, and the floor is yours.
Yeah, so thank you very much. And thank you for inviting me. Thank you for Ravi for the presentation. So today I will talk on one of our recent works on the topic of that calls on recoverability of graph neural network representations. This is joint work with a batch of great collaborators from Habana and Technion, including Avi and Ron Banner and Maxim Fishman and Evgeny Zheltonorsky and myself. I also, a bit about myself, as Avi told, I'm a Technion graduate. Did my master and PhD in Technion. PhD was also only mostly focused on machine learning algorithms. And after 1 year of postdoc position, I started to be adjunct senior lecturer and senior research associate at Technion. Also, I'm involved in industry. I was involved in 2 times as a research intern in Intel labs, and for now I'm involved in. I'm also consulting some leading AI companies about technology and research. So my talk today will focus on how. We will talk about the why we need graphs and what the major pitfalls from being a graph neural network to be great. I will show you our metrics that we proposed for estimation of how graph can be learned. So we hope that this work also will lead more future works that can better represent graph learning. So why we need graphs? So there are a lot of problems that cannot be defined over grid structures, such as images can be. Graphs is a universal language for describing any data, and also it's a shared vocabulary between different fields like computer science, social science, physics, economics, biology. Today we have a lot of available data that we can consume from our and require from our mobile, web, health and medical data, and it can lead to very high impact. That impact can be by designing new drugs, identify some problem in social networking, and also social media. So a lot of domains that are now their data represented by graphs. As I already said, it's also social networks, economics, website and citations, etc. So for now, we can divide graph learning for 3 major topics, for 3 major categories. First is node property prediction. In node property prediction, we want to predict a type of given node and asking about its questions. It can be regression or classification. The second one is linked property prediction. In linked property prediction, we want to predict the correlation between two and asking questions how one node linked to another node. It can also be or regression or classification. And the third one is graph property prediction, whether we can conclude we have some asking questions about entire graph. So let's start from in our talk we will focus on the first task, node property prediction or node classification. So also the research, the specific research was done on this task. But of course, it can be extended also for another task. So let's start from example of node classification. So here we have an example. While we have here two classes, it's binary classification. We have two labels. One is the yellow, and the second is purple. So what we want to do here is to having a partial node labeling to predict the missed labels. Actually, we want to solve here a semi-supervised problem. So yeah, in real life example is can be like as you can see here. If this is a graph represent protein-protein interaction, where the nodes are molecules and the edges and the edges their interaction. So we want to predict here the molecular property. Okay, good. So in link prediction, we want to predict the correlations between two nodes. So in this task, we're looking on pairs of nodes and predict how they're related. In real life, the example is content recommendation. So in content recommendation, we want to recommend to consumers different products. So also there are a lot of different, another additional examples. So the major challenges that we are focusing on this, so the major challenges that encourage this work is the following. So current graph learning approach struggle from efficient capturing of the essential graph information to embedding representation. The problem, so we have aggregation method expressiveness, whether we cannot, whether our function cannot detect or create the essential embeddings. The second one is the lack of ability to propagate information with distant nodes in the graphs, whether there are nodes, they are very more than one hop. One from another, and the third one is that the large graphs they consumes too much memory, and this is this problem this obstacle make them their deployment on any hardware unfeasible, and hence efficient of GNN specific. And for solving that, we should use and develop efficient graph neural network specification methods. So once we understand basically what is graphs and how and what is the major problems for now that are we want to tackle in this work, I will define the definition of the recoverability for graph neural network. Here we describe the basic message passing in node property prediction. So it's a basic mechanism how we're creating an embedding of each node by aggregating the information from his neighbor nodes. Okay, so we are collecting information from neighbor nodes and after that we apply aggregation function on them. Once we did it, we can use a multivariate perceptron or linear layer, we call it, with some non-linearity function. This process is give us to create embedding, and this embedding this embedding we can of course using a classifier or regressor to solve the task. So this process is done for all nodes in graphs. So for all nodes in graphs, we are creating an embedding and applying nonlinearity, and in this manner we are learning graph node properties. So for analytic purpose, we separate the creating of the node embedding part from the classification part. Okay, so here, as we can see, we have first we create embedding. So we have graph G with node feature distributed that acquired to a random variable that we define by X. Okay. And our embedding is actually we aggregate information from the neighboring nodes and generates random variable H. So H is the output. It's the random variables that represent the output once we have create the embeddings from aggregation function. Then we asking question, we using our classifier for predicting given embedding H predicts Y. So this is the typical classification problem. Great. Once we splitted the aggregation function itself from the classification, we will define our metric. So suppose we are given F, which is the best predictor that can predict for given data the output. So we want to define the raw. Well, the raw we want it captures how well we can predict Y given sample X. So different aggregation methods produce different random variables and thus have different values of raw, which give us different metric or different information regards how well we can predict the given label or the given output. So thus a raw we can use it for evaluating embedding quality without using training by looking on the embedding. So CH1 is the collection of all random variables which are fully recoverable from H, whether the raw is 0, it means it's perfect. So CH1 is CHI is the set of all random variables that we can fully recoverable from H1. So in specific example, CH1 is the raw distance is smaller, hence we can better recoverable this subspace using our function rather than CH2. Good. The problem is that we cannot find raw directly from its definition without F. So we propose here is algorithm for efficient estimation of raw, having embedding H and output Y. So we're using RKHS embeddings, universal kernel. For more information of definition, you're invited to look on our paper. And now we don't need to calculate straightforward F to computing row. So we are actually proposing, and this algorithm is fully differentiable. So it can also be very efficient for estimation. Great. So once we can efficiently calculate row, we having the second algorithm that is embedding method quality. So if we can measure embedding quality that we generate sample from our from H and calculate row star, while our row star correspond to better embedding. Okay, so we want to minimize the row star, and in that manner we will creating better embeddings for for our specific task. So it's actually some auxiliary metric for understanding how well we can learn our graph. Good. So once we define our metric, our method, now I will show you different experiments where we can integrate our metric for help for solving the specific problem. Okay, so the first one is we did evaluations when graph neural network can work better than MLP. So homophility. So here we have different data sets. So X are node features before aggregation, and H are node features after aggregation. So as you can see, the row for H is lower than the row for X. So that means that we are having better approximation of our learning graph. So what explains why graph neural networks can be efficiently trained on these data sets. Okay, and we also added for these data sets their homophility measures. So homophility is measured the similarity of the neighboring node classes. From this experiment, we can also observe that the data sets which can have lower homophility cannot be learned for specific embedding methods. So actually, homophility is one of the major pitfalls of efficient embedding learning. Okay. So this is another experiment. So here we can see that we have a correlation between row and the final test accuracy of specific tasks. So we have here two data sets. As I remind you, we are talking about node classification. So we have one data set is called OGB archive. So it's data sets of citation authors and the paper citations. And the second is for PPI, protein-protein interactions. We tested for different graph neural network algorithms, like such as GraphConf, GCNConf, GraphSage, and etc. And we see that we have straight correlation between the raw and the test accuracy. So it means that our metric can efficiently predict what will be the final accuracy of our graph task. Good. So now we'll talk about specification. So as I said, making pruning graphs is very essential for deployment of large graphs on a dedicated hardware. So this experiment, what we have done, we actually have different data sets, and we used two different specifications, random and max D. We dropped 19% of the edges from the graph. And for two different specification methods, we observed that we have highly correlation between our raw that we measured on embeddings and final accuracy. Hence, our method can help to design the specification strategy. So here we also we can see experiment whether we have we are actually can help raw for understanding how well we can learn in a scenario where we have deep network. We have here two scenarios, 3 layers of graph neural network and 8 layers of graph neural network. So as you can see, for the where the raw is going down, it means that using more layers can help us to learn better representations. And when the row is actually increasing over the layers, it means that adding more layers, we can actually have another problem that calls oversquashing. It means that more layers give us worse representations, and it cannot be learned. So also row is very efficient for oversquashing, detecting oversquashing over the graphs. Okay, and finally, it's some initial results that we can see that if we add regularization based on raw minimization, we can actually avoid performance degradation while we make network, while we increase network depth. So as you can see here, in the blue curve is actually with using raw regularization, and without is actually the performance is degraded over the using more and more layers. So as I said, it's initial results, and further research is needed. Okay, so thank you very much.
Thank you very much for the interesting talk. We have at least one question in the Q&A. Shmuel asked, I think I just allow Shmuel to talk. So Shmuel, do you like to ask the question, or I will read it? Okay.
You hear me?
Yeah. We can hear you.
I want to ask you how idea that you presented in your lecture can to help to use methods
Yes.
of machine learning for resolution different social problems and disasters.
Yeah. So this is a very good question, Shmuel. So as I already mentioned before, using graph neural networks can help to expand machine learning methodologies, to beyond grids. It means that for now, people use machine learning for and the successful stories of machine learning is limited to to information that are represented, that have special correlation, what we call. Yeah, so it's video, so it's sound, images, and text, but the real problems, and as you already mentioned, COVID and the disasters or another problems, they ask, yeah. So any other problems, they cannot be that their data cannot be represented by simple grid. It means that each of the points in specific data have no correlation, or it's have correlation, but it's not continuous. So hence, using graph neural networks will allow us to also use machine learning for more tasks. And these tasks are that you are mentioned, they are for sure are can be solved by graph neural networks. And again, our work is we want to improve. So what I said that graph neural networks learning for now it's only it have some pitfalls, and there are still the mechanism there is still in work, and and we need to find the way how we can do it more efficiently, to better represent, to better extract their data, to make these algorithms more efficient. Our work is aided to make them more efficient. Okay, so I hope that I answered your question.
Thank you. I want to add one more comment, one more thing, and one announcement. First of all, there are many problems which are naturally represented by graphs. For example, we are doing some work on reverse engineering because netlist is naturally represented by graphs. We are doing work on as you said, disaster recovery because all the connections are well represented by graphs. So it is natural to think that graphs are very basic data structure to represent the problem, and we try to reason about the problems which are represented by graph, and this is the direction of the new trend, not to talk only about pixels, but to talk about a graph connection, etc. So this is part of this direction, and we strongly believe that it will be more and more important in the near future. So thank you, Chaim, for the exciting talk. This is the third webinar. Soon we'll send a link. We just established a website that we start putting all the material, slides, videos, etc. We'll send you more details soon. I just want to mention that the next talk will be next month by Michael Kagan from NVIDIA, a senior VP and strategic planner there, that will talk about whatever I like to talk about,